All right, so I cut that off a little too fast. A couple things to look at when your growth factor is over 1. When you are doing your constant multiplier and it's over 1, then it's growth. If your growth factor is less than 1, then it's decay. And that's what I wanted to show. But and also down here, they talk about decay when the constant multiplier is less than 1, but it has to be greater than 0. So not a negative value, just between 0 and 1. It'll be fractional. Like this is 50%, where this is like 150%. Okay, so just want to finish that up, and then we're going to move to page 2. This is where we actually get into the good stuff. So on page 2, we're actually looking at the general growth formula, and it has some notation in it that you need to know. The first thing you need to know is that A of t represents your time after. So this is like the amount that you're going to get after time has passed. A sub 0, this is also called A naught, is your initial amount. So this is your beginning amount. That's super important that you know that. And then R represents the rate. And then T is time. And T is an exponent. And when we start to do compounding or in cycles, this is going to be the number of time periods. Okay, so what I want you to do is take a look at example 1 with me so we can kind of figure this out. It says college tuition costs are rising about 5% per year. That would be the rate. Okay, so when you get a rate as a percent, you've got to convert it to a decimal. If you're not sure how to do that, take your percent and divide by 100. So 5 divided by 100 is 0.05. But it's rising. And when it rises, that means that it's got to be over 100%. So we have to add a 1 in there. So it's going to be 1.05. Remember, growth, it has to be larger than 1. So we have to put the 1.05 to get that to happen. So that's where this comes from. The 1 stands for the growth. The 1 plus stands for growth because it's got to be greater than 1 in order for it to grow. Current tuition is $12,000. What's it going to be in 4 years? So this is our beginning amount. So this is what we know right now. That's A naught, or our initial amount. And that's why that is here. And they want to know what's it going to be after 4 years, and that's our period of time, so that's our exponent. So all we have to do is, in our calculators, type in 12,000 times 1.05, and you're going to raise that to the 4th power. Okay, and you're going to hit equals, and this is what you're going to get. So if tuition's rising 5% every year, then a 12,000 normal tuition is going to end up becoming $14,586 and about 8 cents. Okay. Depreciation represents a decay, because depreciate means that the amount of money that something is worth is becoming less and less. It's not growing, it's decreasing. So when it depreciates, it decreases. This one is decreasing by 20%. So the thing that you need to know is that for our rate is always with what we have, not what we don't. And if this says that you're decreasing by 20%, then you have to figure out what you really have. So you have to take 1 minus your 0.20 to figure out what you have left. This is what you're going to work with. So you're losing 20%, which means you only have 80% to begin with. So this is going to be our growth factor. And it's our growth factor because when we have a depreciation, or if it's a decrease, then you have to subtract 1. So that's why this is happening here. We're subtracting from 1 because it is going down. You add 1 when it's going up. Growth, you add 1. Decay, you subtract from 1. The farm equipment that they wanted to buy was $425,000, and they just want to know what's it going to be worth after 10 years. So they are financing this piece of farm equipment. So $425,000, and it's only retaining 80% of its value. It's lost 20%, so it's retaining 80% of its value, which sounds like a lot. And we want to know what the cost is going to be, or what it's going to be worth in 10 years. So we're going to go to calculator, and we're going to put in 425,000, and we're going to do times 0.8 or 0.80, and we're going to raise that to the 10th power because this is how many years they want to look at. And when you see this, oh my goodness, this is craziness. $425,000 piece of farm equipment in 10 years is only worth $45,000. That's what 20% depreciation does. It takes a $400,000 item and reduces it to $45,634.03. That's crazy amount of money lost. So that's kind of like one of the struggles of farmers, is that their equipment isn't worth anything over time because of the depreciation factor. So now that we looked at a growth and we looked at a decay, now we're going to do some practice. The first thing we need to do is decide if we are doing a growth or a decay model, and then we can put it into the formula. It says the price of gasoline is expected to rise. So this is a rise, so this is a growth. For growth, don't forget that you have to do 1 plus whatever your percent is. This says that it's going to grow about 1% per week. 1% as a decimal is 0.01. So that's going to be our growth factor. Our growth factor is going to be 1.01. The original amount that the gas is our now price, which is $2.68. So we're going to start with $2.68. This is going to increase by 1%. And we want to know in a time frame of 8 weeks, what's it going to be? My dog is freaking out. So again, we've got $2.68. It is increasing by 1% for 8 weeks. 2.68 times 1.01 raised to the 8th power because we want 8 weeks. And it's going up to $2.90. So that's a big jump in gas. So a 1% increase doesn't sound too bad, but 8 weeks later, that's a big jump for gas per gallon. So that's number 1. Taking a look at number 2, we're looking to see if it's a growth or a decay model. On average, the population of Smyrna High School has increased, so that's a growth, by 3.5%. So we know that this is going to be a growth, which means we're doing a 1 plus, and 3.5%. Now, if you're not sure how to do the decimal equivalent of this, like I said, all you have to do is take 3.5 and divide by 100. So it's 0.035. Make sure you do that right. And that's going to be our growth factor. So our growth factor is going to be 1.035. And just for the record, population is always growth. Always, always, always. It's always exponential, and it's always growth. That's a go-to. So keep in mind that that's like a realistic where growth models actually come from. Current, which is like what we have right now, is 1,552 students enrolled. That's a little low. We're up to nearly 1,800, I believe now. So, but we'll use this data. 1,552 is the now. We are growing at 3.5% increase. And we want to know what's the enrollment going to be in 5 years. So this is how we predict when we need schools. We use a growth model to determine, based on current trends, how many students are going to be in the building. If the population is 1,552 in the high school, what's it going to be in 5 years? So 1,552, 1.035 raised to the 5th power, and we're up to 1843. So in 5 years, we are going to increase by almost 300 students, okay, at a 3.5% increase. Let's take a look at number 3. Number 3's got a little bit going on here, but I think it's worth it. I think it's worth us looking at. So in number 3, the new car costing $20,000. So that is our original price. And that's not a real fancy car. That's kind of a base model, little hoopty. Is going to depreciate by 20% per year. So we need to figure out what these values are. What we're going to do to complete the table of values is we're going to write our function equation, and then we're going to plug in the years and get the values. So what do we know? Well, it's depreciating by 20, which means that we have 1 minus 20%. Remember, depreciate, you have to subtract, and we're subtracting off the percent. So we have 80%. That's what we have to work with. This is going to keep 80% of our money, just like the tractor or farm equipment, excuse me. So what we are going to do is figure out what is our original. Okay, we started with 20 grand. It's keeping 80% of its value. And what's it going to be worth after the first year? So I'm filling in for the first year. So 20,000 times, oopsie, let me do a parenthesis instead, 0.8 raised to the first. And now it's down to 16,000. So the first year it loses $4,000 in value. Now I'm going to try for year 2. So I'm going to take my original. This is keeping 80% of its value, and we are going for year 2. Year 2, we're down to $12,800. So I haven't even touched that amount in my payments. But 2 years later, from a $20,000 car is now only worth $12,000. Now we'll look at year 3. So 20,000, 0.8 raised to the third, 10,240. Okay. So in 3 years, we've lost almost half of the cost of the vehicle in 3 years' time. And this is normal. This is normal. This isn't just for a math problem. This is like normal life stuff. 4 years later, most people take out loans for 5 or 6 years or 7 years, depending on how much their car is worth. We're going to the 4th because we want 4 years down. Now it's only 8,192. 5 years in, we find a green. So let's say I paid this thing off in 5 years and I was ready for a trade. My car will only be worth $6,553 and 60 cents. Can't forget that. So I'll trade my vehicle in after 5 years of taking care of it. This is what my max will be, because that's all the value of the car. That's like the Kelley Blue Book. And then we've got one more. Let's go purple. So 6 years in. $5,242 and 88 cents. Okay. So 6 years after a brand new car, and you are down $15,000. Okay. So I want us to take a look at the graph. And the reason why we're looking at the graph is because you need to see how the graph actually moves. All right. Because we have to answer the question, why is this graph different than the population growth graph? So this value is in thousands. So this is 2,000, 4,000, 6,000, 8, 10,000, 12, 14, 16, 18, and 20,000. And this is what the car is worth when we bought it. 0, 20,000. 1 year in, and we're at 16. 2 years in, we're at 12,800, so almost halfway. 3 years, we're down to 10. 240. So it's kind of hugging the 10 line. 4, we're at 8. 192. So it's right on that line. 5, we're at 6,500. So this is definitely not linear, and I'll show you why it's not linear. Let me take my paper so I can show you that if it was linear, it would look like this. See? It doesn't do that. This is exponential, or it's a curve, because it's coming out like this. Now it's very subtle, because you can draw a line and be like, yeah, that's linear, but it's not. This is not decreasing by the same amount every time. And you can tell because between 5 and 6 years, it looks like it's not even moving 2,000. Whereas 4 and 5 years, it's moving a little less than 2,000. But up here between 0 and 1 year, it's moved 4,000. So, 4,000, then 3,200, then, so it's not constant. So this is definitely a curve. It's a curve. It's not straight. It's a curve, but it's very slight. So it's not as aggressive. It doesn't shoot up really fast as far as like an explosion. There's no explosion in the graph. There is a decrease. This is a decay model, so it's decreasing. And the biggest difference in your decay model happens in the first section. That'll be the biggest jump, will be at the beginning. The biggest decrease will happen in the first jump. Okay? But it is still a curve. It is definitely a curve. It is not linear. Okay? So I'm going to stop here, and then we'll go ahead and take a look at page 3.